Okay. So we have already discussed about for energy signal time autocorrelation function, and we have also proven that whenever we take the Fourier transform of time autocorrelation function, that becomes the energy spectral density. We will just try to see, we have also discussed in one of the previous class the modulation. So let us try to see what happens to means whenever we modulate a signal, what happens to the energy of it and the corresponding energy spectral density. Okay. So let us see, we have a signal GT, which is again time limited, and we want to generate a modulated signal or a frequency shifted signal, which is nothing but GT multiplied by cos 2 pi f0 t. So we have seen already that if we multiply by cosinusoidal, it gets frequency shifted in plus and minus as well as, and the corresponding signal is called the modulated signal. Okay. So I want to now evaluate the power spectral density of this phi t, right. So basically what I wish to do is the psi of this phi t, which is the power spectral density of this one. Okay. So first of all, if we wish to do that, there is one technique we have already told, that if I can get the Fourier transform of this one, that is something we have already evaluated. If GT we know the Fourier transform is capital GF, then immediately we know that phi f should be half GF plus F0 plus GF minus F0. This is something we have proven in one of the previous class, right. So that is the frequency shifting property actually of Fourier transform. So if I know this, so basically I know the Fourier transform of this one, all I have to do is take mod and square. So that should be modulus of half G f plus f0 plus G f minus f0 square. So that means 1/4 right. So if I just try to put, suppose GF was something like this, of course what we are saying that the signal is you will later on see that if a signal is time limited, then it will not be bandwidth limited. Okay. So it will have frequency component up to infinity whenever a signal is time limited. But what we are saying that probably it has an effective bandwidth. That means the other component that it has, RDR whatever we have discussed, if GT was something like this, a time limited signal, then GF we have seen it has all the other lobes, side lobes. Okay. So we are saying that those are insignificant. Okay. So the signal is having effective bandwidth up to this. Okay. As long as the signal looks like this, then if I modulate, so that phi f will look like at f0 there will be this one, at minus f0 there will be this one. Okay. If f0 is sufficiently large compared to its bandwidth, effective bandwidth, then what will happen, these two things will not have any overlap in frequency domain. Okay. As long as that is happening, so this is actually characterized by this one and this is characterized by this one. Okay. So as long as these two are non-overlapping, their square, the cross product should be 0 because they are non-overlapping. So I can always write, if that condition is true, that f0 is much bigger than the bandwidth of the signal, okay, or effective bandwidth of the signal, then I can write this square must be just summation of 2 square. Right. So that is what we get. Now if I just talk about, suppose GT was having a measurable quantity which is Eg, let us say that is the measurable quantity. It might be interpreted as minus infinity to plus infinity integrated g square t in time, or mod g square f or mod gf square integrated from minus infinity to plus infinity. Okay. So, anyway that is the Eg, right. So, if that is Eg, this if I integrate over frequency band. So, suppose I wish to now calculate the energy of this signal, the modulated signal. So, E of phi, that must be integration of this energy spectral density over the entire frequency. Okay. So, that integration should be 1/4 integration of this one plus integration of right. Now, this integration is just equivalent to Eg, because it is nothing but the same Gf shifted, right. So, same Gf shifted, if I just integrate mod Gf square, that must give me same thing. So, this must be a Eg, this must be also a Eg. So, what do I get effectively? 1/4 Eg plus Eg. So, that means my energy becomes Eg divided by 2. So, that must be the E phi. So, always remember, this is going to be very essential for our analysis of any modulation. Always remember, whenever we modulate, that means a signal is multiplied by a cos of unit amplitude, always the energy gets half due to the process of modulation. That is a very peculiar thing. You might be asking why this is happening. I am having a signal Gt, I am multiplying that signal Gt by another cosinusoidal, and by the process of this multiplication I am losing energy. You know what actually is happening? It's very easy to understand. So, where the energy is getting lost, it's because suppose I have a signal. Let us say that signal is just tone. Okay. So, it's just a cos omega mt. Okay. So, whenever I multiply this signal with another higher frequency signal, okay, let us say that is cos omega 0 t. Okay. Once I multiply, what happens? Basically, it will be looking like this, cos omega m t into cos omega 0 t. So, this particular term becomes actually the amplitude of this cos omega 0 t, because cos omega 0 t has higher frequency. So, means if you see this one varying, this will be varying at a very higher rate, while this one is varying, this will vary at a very low rate. So, therefore, actually you can interpret it as if this is varying and the amplitude is slowly varying with respect to this one. Okay. So, eventually what will happen? It is a cos omega 0 t, only the amplitude will have this envelope. So, it will look like this. Sorry, let us try it one more time. It will look like something like this. Okay. So, what is happening now? You can see earlier it was a cos omega mt, whatever energy it was having, or it might be just a square wave, whatever it is, whatever energy it was having. Now, what is happening? That particular part, suppose if it was just a pulse train, then after modulation it will look like this. Inside that there will be this cosinusoidal, again this inside that there will be cosinusoidal. So, what is happening? Earlier it was almost keeping that same level of amplitude, So, the energy if you integrate, okay, it will be much more, whereas here there is a oscillation. So, the energy is getting degraded due to this modulation, due to this oscillation, okay, which is also true if you just see the RMS value of cos, that is always 1 by root 2. Okay. So, the power if you wish to calculate, that is half. So, basically whenever you multiply, it is getting multiplied by half. So, whatever it is, the reason means there might be multiple reasons that we can state, but what happens, always remember that whenever you multiply with a cosinusoidal or a sinusoidal, your energy will be degraded. It becomes half of the original signal energy. That always happens. Okay. So, this is just to demonstrate the utility of, or how to utilize our energy spectral density. Whenever we do some modulation or some modification of original signal, what happens and how do you evaluate again the energy spectral density. So, it is just to give an example. There might be multiple such example, and we can take all of them as homework. Okay. So, what now we wish to do is, we wish to do the similar thing for a power signal. Okay. So, now let us say we have a power signal GT. It might be periodic, it might not be periodic, whatever it is. Power signal means, first of all, it is stretching from minus infinity to plus infinity, and it has energy that is infinite, because it is stretching from minus infinity to plus infinity, but it has a finite power. That means over a if you just calculate the energy for the entire time duration from minus infinity to plus infinity and divide by t, you will always get a finite value. So, it has a finite power, but infinite energy. So, that characterizes for power signal. All periodic signal are power signal. Okay. So, if I have a power signal, okay. Now, we have already stated that the power must be calculated like this: limit t tends to infinity 1 by t integration minus infinity, sorry, minus t by 2 to plus t by 2, okay, g square t dt. That means I am almost trying to evaluate the energy, but divided by time. So, what I am doing, I am taking a valid t or finite t, calculating the power. So, calculating the energy, dividing by t, and then all we are doing is stretching that limit to infinity. Okay. So, that was our definition of power. Earlier we have done that. Okay. If this is real signal, if this is a complex signal, then this should be mod gt square or gt into g star t. Okay. So, that same thing. So, this is all good. What now we should do? Suppose I have a power signal. First thing I will do, I will truncate that signal. So, I have suppose a power signal which is stretching from minus infinity to plus infinity. I first define a t, and I define a signal GTT, which is defined as GT if t is, or I should say mod t is less than or equal to t by 2. So, if this is suppose 0, that is minus t by 2 and that is plus t by 2. So, I have truncated with a t centering at 0, and we are saying that GTT will be exactly equal to GT. So, it just carries the property of GT from minus t by 2 to plus t by 2. Rest of the places it is 0. So, that is truncation. So, that means the whole signal up to t I am just taking, the rest of the things I am making 0. Okay. So, that is my new definition of signal, right. So, what we are trying to do again now, you can see means in Fourier transform we keep on doing that. Earlier we have derived Fourier series. From Fourier series we have actually taken it to Fourier transform, because Fourier series was defined for power signal, or I should say periodic signal. Then from there we wanted to derive something for time limited signal or the energy signal. So, we have again used that truncation property. Here also we are almost doing that. Earlier we have defined energy spectral density. So, energy spectral density was defined for a energy signal which is time limited, right. So, now we have got a time means unbounded signal. So, it is defined from minus infinity to plus infinity. So, what we are trying to do, we wish to employ the same thing again. So, we are now first truncating the signal and then we will put the same trick, t tends to infinity, right. So, this truncation, if I put t tends to infinity, gtt goes to gt. So, if I just say gtt limit t tends to infinity, by definition it should be equal to gt. So, this particular thing I know, but eventually what has happened, the gtt that I have defined, that is actually now a energy signal because it is truncated. So, it must have a finite energy as long as some of the portion are not going to infinity or some of the portion are not blowing up. Okay. So, as long as the signal is characterized by that, which was also the characteristics of gt. So, therefore, I must always get a energy signal by doing that truncation. Okay. So, by definition now my gtt is an energy signal, right. So, now this pg I can define as limit t tends to infinity 1 by t minus t by 2 to plus t by 2. See, this integration is defined from minus t by 2 to plus t by 2. So, instead of g square t I can write also gtt square, that will give me same thing. These two are equivalent according to my definition because gtt is exactly equal to gt from minus t by 2 to plus t by 2. My integration was always being done from minus t by 2 to plus t by 2. So, therefore, gtt if I integrate or gt if I integrate, both will give me same result. So, that must be pg. Okay. So, if this is the case, now you can see for this gtt, this particular part, because it is a time limited signal, that must be the energy, right. This is the energy of that signal. So, I can immediately write limit t tends to infinity 1 by t, this is I can write this as EGT, that means energy of that truncated signal, I can write this. So, PG is nothing but this thing. Okay. Only thing is that earlier PG was defined for GT, now PG is defined for a truncated signal where I have the energy. Now, the good part is this energy, because it is a truncated signal, so it is time limited, I can actually now relate this to energy spectral density. Okay. So, I can immediately write this as limit t tends to infinity, okay, 1 by t. I can put this EGT as, if I have this GTT, that signal, if I take a Fourier transform of that, that should be GTF, and if I take mod of that, and if I do an integration over full frequency minus infinity plus infinity, that must be my EGT, right. This is well defined because I have now evaluating it for a energy signal. So, I should be able to write this. So, immediately I can write instead of this minus infinity plus infinity modulus of GTF square df, right. So, this is something I can always do, fine. If this is the case, now this t has nothing to do with this f, right, I can take all these things inside. So, I can write minus infinity to plus infinity limit t tends to infinity mod GTF whole square divided by t, this whole thing into df, right. So, what I have got eventually, the power is now related to this, where I have this particular part, this I can call as the power spectral density, because what is happening now, similarly like the energy spectral density, I can, this is defined as a, of course this is the energy spectral density, so it should be a spectral density. So, this if I integrate over entire f, I actually get back my power. So, that must be defined as power spectral density of my signal. So, I can now write that, suppose power spectral density is defined as SGF. So, that I can write as limit t tends to infinity mod GTF whole square divided by t. right? Good. So this is actually the definition of a power spectral density. So any signal GT, if you are willing to define the power spectral density, what you do, you truncate that over a T, evaluate the Fourier transform, get modular square, that means the energy spectral density of that, and then you put that T tends to infinity, that energy spectral density divided by T. So that must be my energy spectral density. By definition, we have seen that. Okay. And we have also proven that if I integrate this over F, the entire F domain, I will be getting my power back, right? And that is why it is called power spectral density. Okay. Again, it should be related to autocorrelation function. So what I wish to do now is I wish to define the autocorrelation function for a power signal. Okay. So that is Rg tau. So what will happen, because it's a power signal, so just multiplying the signal and its delayed version and then integrating will give me always infinity. Okay, because that's very obvious. If I just put tau equal to 0, immediately I get g square t integrated over minus infinity to plus infinity. That's already, I know already that energy is infinity. So there is no point in evaluating that. I should be evaluating it in terms of almost similar to power. So what I will be doing, again I will be doing similar thing. I will be putting limit t tends to infinity, I will take 1 by t and then I will integrate minus t by 2 to plus t by 2 gt. Okay. That is now the definition of time autocorrelation function for a power signal. Okay. Because for power signal, if I do not do these things, I will always get infinity value. Okay. So I have avoided this, but remember this is just a definition. Okay. Why we have defined it this way? Because we will now see that if I do a Fourier transform of this, again similar to the previous one, we will get back our power spectral density. So this is what we will be trying to prove now. Okay. So let us try to see how do we define that. Okay. So this is my Rg tau. Okay. I can put this as limit t tends to infinity 1 by t. So this integration, what I can do now is, instead of minus t by 2 to plus t by 2, I can put this integration from minus infinity to plus infinity, provided I put the truncated signal over here. Okay, instead of gt, because gt is defined from minus infinity to plus infinity. Okay, this integration allows me to do from minus t by 2 to plus t by 2. So if I just truncate that, then I am still limited within that t only. Okay, so therefore I can always take this, stretch this integration from minus infinity to plus infinity, as long as I am applying this. Okay. So this is good, no problem in that. Now let us see what is this. This is actually for the truncated signal time autocorrelation function, which is the energy signal. We already know that. Okay. So if this is the energy signal, then Fourier transform of this one must be the energy spectral density. So this entire thing has a Fourier transform pair, or I can say they are paired by only this part, not limit t tends to infinity and 1 by t, not that part. Only this part has a Fourier transform pair, which is GTF whole square. I already know that. Therefore, this Rg tau must have a Fourier transform, because this t has nothing to do, okay, with it, that with Fourier transform. Fourier transform will not have that capital T. Okay. So Rg tau must have a Fourier transform pair, which is nothing but this will be as it is there, only this part will be added. So I will say it is a Fourier transform pair, remember it is not equal, it is just limit t tends to infinity 1 by t GTF mod square. Okay. So, this part is the Fourier transform of this one. Now, what is this? We have already proven that that is SGF. So, therefore, RG tau and our defined SGF are Fourier transform pair. So, we know that for a power signal, now if we, the way we have defined time autocorrelation function, if we do a Fourier transform of that, the time autocorrelation function will be always getting back our power spectral density. Fine. So, this is another very important result that we were trying to get. So, what we have eventually done in these two classes, we could actually, earlier we have done Fourier transform, but Fourier transform was little vague because there was no measurable quantity. Now, from that same part we could actually get a measurable quantity and we could relate that in the frequency domain. Time domain we had that measurable quantity, we knew what is the energy or power for corresponding energy signal and power signal, but in the frequency domain we never had that relationship. What we have done, first we have proven that okay, in the frequency domain also we can get corresponding energy spectral density and power spectral density, which is nothing but if it is a energy signal, then all you have to do is take the Fourier transform of that signal and then mod that square. Okay. And we could also prove that if you integrate over frequency you get the overall energy. For the power signal we just have to do a little bit extra, we need to truncate that signal, calculate the energy spectrum, and then whatever truncation value we have taken, we have to divide by that truncation and take limit that truncation parameter t tends to infinity. That gives me the power spectral density. We could again prove that if you integrate that, you will be getting overall power Pg of that signal. But then we have proven two detours for calculating energy spectral density and power spectral density. One was if we, for an energy signal, if we do autocorrelation function the way we have defined it. If we do autocorrelation function, we know that once we calculate autocorrelation function, immediately if you take Fourier transform, you will be getting your energy spectral density. That is another way of doing it without doing the Fourier transform of the signal directly. You do the Fourier transform of the autocorrelation function. Of course, you will be asking why I am exerting myself to first calculate autocorrelation function, then take that autocorrelation function anyway, again you have to do Fourier transform. We will clarify that in the next class, but that is another way of doing it. Okay. So, you first evaluate that autocorrelation function the way it has been defined. For energy and power signal, both similar thing, only the autocorrelation function definition is a little bit different. So, if you do autocorrelation function of the energy signal, you will get corresponding energy spectral density if you do Fourier transform. If you do autocorrelation of the power signal, then you will get automatically, if you do Fourier transform, you will be getting corresponding power spectral density. Now, the big question is why I need that second path, but remember probably that is the most essential part and most important part to evaluate any kind of realistic signal. Next we will give one example. Without talking about random process, you will probably be able to appreciate why this is so much required.